Right. So crystal field theory I am talking about, and in crystal field theory, what I am saying that till now we have done that the d orbital, this is the stable state configuration. Then we found that few compounds with this configuration also, first three only, this is also stable. And we needed some theory to explain it for that crystal field theory. So what crystal field theory says that D subshell is actually split due to the field, magnetic field. It is split in two parts. First three, these are called T2G, and these two are called EG. These are just conventions. So that's what I have written here before proceeding further. We just need to know that there is a branch of science called group theory. Group theory means we group the orbitals together, in which T stands for triply degenerate, means three are degenerate, these have same energy. And E stands for doubly degenerate, means these rest two will have equal energy. So this is called EG, this is called T2G. This is just convention. Okay? Don't think that this is a specific meaning, this is convention. So it assumes, crystal field theory, CFT means crystal field theory, assumes the ligands to be point charges in case of anions or dipoles in case of neutral molecules. And there is electrostatic force of attraction between ligands and metal atoms or ions. It is theoretical assumption only. Not much important. Only the point you need to remember that the ligands are considered as point charges only in case of anions. If it is neutral molecule, then there is a dipole moment. The 5 d orbitals in isolated gaseous metal atom have same energy, that is, they are degenerate, but I will be talking about in presence of a strong magnetic field, they will get split. So when they will get split, I will talk about that. Don't bother about it. Group theory is just that if 3 orbitals have same energy, we say it is T2G. Other two have same energy, we call them EG. So that is convention, just to denote. I will be saying T2G and EG, you should know what I am talking about. If I am saying T2G, I am talking about first 3. If I am saying EG, I am talking about rest 2. T triply. Triply degenerate. Third one, the d orbitals remain degenerate in a spherically symmetrical field of negative charges which surround metal atom or metal ion. So normally they will remain degenerate, means all 5 will have same energy. All 5 will have same energy. When ligands like ammonia or water approach the central metal ion, it becomes asymmetrical. Then it is not symmetrical, it is asymmetrical. And d orbitals do not have equal energies, which result in splitting of the d orbital energies. So what I am talking about? Ammonia and water, till now I have talked about. So if the ligands are ammonia or water, there are other possibilities also. Okay. Then there is difference or deviation from this symmetrical, or you can say degenerate orbitals. Now it splits. It is called splitting of d orbital energies. The pattern of splitting of d orbitals depends upon the nature of crystal field. Crystal fields are of 2 types. One is octahedral, the other one is tetrahedral. Now it is easy to understand if you understand it for octahedral field. Tetrahedral field, it will be just opposite. It helps to determine quantitative estimations of orbital separation energies, magnetic moments, and spectral and stability constants. And that is the questions I will be talking about. It considers the bond to be ionic and the interaction between metal ion and ligands is purely electrostatic. So what is difference here? Difference from the other theory what we have talked about. What theory we have talked about? Huh? Okay. Hybridization we have talked about. Okay. In which case we decided whether it will be sp3, whether it will be dsp2, whether it will be sp3d2. You remember that? So the hybridization we have talked about, there we did not talk about the electrostatic concept. Okay. Rather, when we started this chapter, I said there are coordinate bonds. That's why we say these are coordinate compounds. You remember that? Okay. But here crystal field theory considers it is purely electrostatic. Tanishi, yes, valence bond theory, correct. And there is overlapping due to hybridization. That's what we talked about. Okay. Now, due to their different electrostatic repulsion with ligands, d orbital splits into two groups which have different energy. The dx square minus y square and dz square orbitals belong to the Eg symmetry. Understand it? What I am saying? Do you remember? We have dxy, dyz, dzx, dx square minus y square, and d square. 5 orbitals named as like this. And I'm just explaining. Sometimes it is asked in the question as well. So remember, if I say I have my horrible drawing. If I say I have the lobes dxy, okay? If I say I am talking about dxy, then it will be in xy plane. Okay, it will be in xy plane, but the lobes will not be along x and y axis. So you need to remember. So xy plane, it will be in xy plane, but the lobes will be somewhere between. So one lobe will be like this, and another will be y and x. Okay. So it will be between x and y, but the lobes will not be along the axis. Similarly, dyz, it will be in yz plane, but lobes will not be along y axis and z axis. Similarly, zx. But if I talk about d x square minus y square, in this case, it will be in xy plane. dxy was in xy plane. This one will also be in xy plane. But in this case, the lobes will be along x and y axis. Clear? So if I have z, y, x, so x axis and y axis. So these will be along x axis and y axis. That is dx square minus y square. dz square, if you remember, was dumbbell in a donut. You remember that? This is dz square. These are the shape. So these two are Eg. And rest three, dxy, dyz, dzx, those are T2G. Those are clubbed together, means they have similar energy and these two have similar energy. Any confusion here or any question here? So these dxy, dyz, dzx orbitals belong to T2G symmetry and they are more stable. Lower energy means more stable. I will show you the diagram as well. It will be more clear. Then the energy difference between the two sets, which one? T2G and Eg. So Eg is less stable, T2G is more stable. I am talking about octahedral field. Remember, I am talking about octahedral field. Whatever is for octahedral field, for tetrahedral field, it will be opposite. So octahedral field I am talking about, I said that T2G is more stable. It will be on lower side, Eg will be on higher side because that will have higher energy. T2G will be more stable, Eg will be less stable in this case. The energy difference between the two sets of D, means energy difference between T2G and Eg, is known as ligand field splitting parameter and it is denoted by delta naught. ligand field splitting parameter. Okay, it is also known as crystal field splitting energy, where the subscript O refers to the fact that it is an octahedral field. It means if you see delta T, that will be for tetrahedral. Same thing. What is this parameter? Delta naught. This is energy difference. Nothing else. Energy difference. Now, first see the diagram. Okay. So you have in free ionic state, this is the D subshell. In presence of octahedral field, okay, octahedral field, it will acquire some energy. It will increase its energy, overall energy, and then it will get split into two sets. One set will be T2G, other set will be EG. So this diagram is just showing that this is in absence of crystal field. This is in presence of crystal field, and in presence of crystal field, it further splits into two forms. T2G is stable, so it is lower energy. EG is less stable, so it acquires higher energy. But the sum of these two has to be equal to this one. Sum of the energy here and sum of the energy here will be equal to this energy total. It means you have three orbitals here, that is multiplied by 0.4, and it is two orbitals multiplied by 0.6. So whatever is positive and negative will be same, they will get cancelled out, and you will get the average here. This average is known as barycenter. Okay, so if you come across what is barycenter, this is the average of the T2G and EG energies. Why the difference from the normal? The difference here is 0.4 delta naught, because this energy and this energy should cancel each other. Only then they will be at the center. Here we have three, so each should have 0.4, 0.4, 0.4. Here we have two, it should have 0.6, 0.6. So you see both have 1.2. They will get cancelled. Okay, so that's how we write it. It is actually 0.4 and 0.6. That's why it is written as. Otherwise, we could have written it as 0.2 and 0.3 as well. Okay, so it is actually 0.6 times and 0.3 times of delta naught. So that's why we say that 3 times minus 0.4 plus 2 times plus 0.6 delta naught will give us 0. If we talk about delta T we can get with this formula. It is 4 by 9 times of delta naught. So if delta naught is given, but the question is talking about delta T, you can use this formula to get the value, or vice versa also. The crystal field splitting delta naught depends on this is crystal field splitting energy. Okay. So CFSE, it is in short form, it is used as CFSE. So wherever you see CFSE, it means we are talking about delta naught. If it is octahedral, delta. No, in both cases it is CFSE. If it is subscript O for octahedral field, subscript T tetrahedral field. So depends upon the field produced by the ligand and charge on the metal ion. Some ligands are able to produce strong fields in which the splitting will be large, whereas other ligands produce weak fields, which results in a small splitting of d orbitals. And this is the same thing what we talked about. In which case, strong, we talked about this thing. Weak, sorry. And strong. Okay, so increasing order of CFSE. You must remember this. It will be used very frequently to answer these questions. Questions are not tough. sometimes the theoretical question becomes tough if you don't remember the points. Otherwise, normally the questions are not tough. For complexes in a ligand field, d orbital occupancy depends on delta naught and pairing energy. This one is very simple concept, right? The concept is very, very simple. For each complex, there is some delta naught. Now here in this case, we are deviating from the concept of pairing, but it is almost same thing. If I go back here, we said that if we have any of these ligands, strong field ligands, then pairing will take place. Here we are saying the same thing. Here we are saying if this is the case, then the pairing energy P will be less than delta naught. Means whatever is this energy, okay, then it is greater than pairing energy, then it is considered as a strong field ligand, and in that case electrons will pair up in lower energy d subshells first. The only difference, as I said earlier also, the difference is in the terms of T2G and EG. Otherwise the concept is very much similar. We are still saying that if it is a strong field ligand, pairing will take place. But here now we are saying that if it is a strong field ligand, then its CFSE, crystal field splitting energy, means this energy difference, delta naught, okay, is greater than the energy required for pairing. So P is that much energy which will initiate pairing. If this splitting is greater than that energy, then certainly pairing will happen. So for a complex, there is pairing energy. If this splitting energy is greater than that pairing energy, then pairing will happen. So that's why electrons pair up in lower energy d subshell first. And these form low spin complex. What is low spin complex? Try to understand. Suppose you have this configuration. This is called very high spin complex because the spin is in just one direction. All are non-paired. But if there is ligand out of these ones, then it will create the splitting of the d orbitals, and delta naught will be greater than P. In that case, what will happen? Pairing will take place in these three orbitals. So what will happen? Instead of this configuration, in presence of that field, these two electrons will move to here. So now the unpaired electrons only one. So it is low spin. So the question is which one will be high spin or low spin and why? This is the reason. You will say the ligand is strong, the splitting energy will be high, that will be greater than the pairing energy. Pairing will take place in the lower d orbital, 3d orbitals. These are lower 3d orbitals. So the configuration will change from d5 to T2G, here 5, EG 0. Earlier the configuration was T2G3, EG2. D5 is actually T2G3, EG2. Total 5. But now the configuration changed to here in T2G you have 5, In EG, you have 0. So this question can also be asked, what will be the configuration? You will use this concept. It will be, why it will be low spin complex? Due to a strong field, there will be pairing. If it is weak field ligand, then pairing will not take place. Forms high spin complex because pairing will not be there. High spin complex. These points you need to remember. The magnitude of CFSE means crystal field splitting energy for most of the complexes is of the same order as the energy of photon of visible light. That's why sometimes it is asked why, and this theory explains the color in the complex. So most of the complex are colored compound. The reason is because in this case, the energy CFSE is in the range of visible region. So if this question is asked, the answer is of just one statement. The complexes or coordinate compounds are colored because the crystal field splitting energy is in visible region. Hence, whenever DD transition takes place, it imparts color to its complex. The color of the complex is the color complementary to the wavelength absorbed. So if the wavelength absorbed is blue, the complementary color will be red. You will see it as red. So if it is yellow absorbed, you will see it as green, like that. Now tetrahedral field, as I said, whatever is applicable for octahedral field, for tetrahedral, it will be opposite. So in this case, what will happen? You will have EG here and T2G will be at the top. So here EG will be more stable, T2G will be less stable. Other concepts will remain same. Here it will be 0.6, here it will be 0.4. Those concepts will remain same. Any confusion? Any question here?
Sir, where can we use this del T formula?
This formula we use if we need to do conversion from octahedral field to tetrahedral field and vice versa. So in few cases, delta naught will be given, but the question will be about tetrahedral. Yes.
Yes, sir.
Now, stability of coordination compounds. Stability of complex in solution refers to the degree of association between the two species involved. How they associate. Magnitude of the equilibrium constant quantitatively expresses the stability. So you need to just remember the last statement. Equilibrium constant represents the stability. So tell me whether equilibrium constant should be high or low for stability. High, right? Because equilibrium constant is products concentration divided by reactants concentration. So products concentration is in the numerator, that should be high. Stability depends on charge on the central metal ion, that is what is the oxidation state. Greater the charge on central metal ion, more is the stability. This concept has been used quite frequently in competitive examinations, whether it is NEET, whether it is IIT. This concept has been used to answer which one will be more stable. You will use this one and others also. So if you see the oxidation state in the complex, the one which has highest oxidation state, logically that should be more stable. Moreover, we will consider other points as well. Basic nature of ligand, more basic strength of ligand, more is the stability of complex. Can anyone explain why? Why? This one is very simple question. This is asked as which one will be more stable. So you will see that ligand which is more basic. Okay. More basic ligand will make the complex more stable. But why? What is the reason? Anyone? Due to? No. Anyone? No. The reason is, what is the definition of basicity? Basic means it will donate the electrons easily. And ligands actually donate the electron to form the coordinate bond. Do you remember that? Huh? No, it's not about repulsion. It's about, yeah, that's obviously the underlying part of it. But what I am saying here, you have metal here. If you have ligand here and it can donate its electron to form the coordinate bond, then it will be more stable. If ligand cannot donate the electrons, coordinate bond will not be formed. And it can donate the electrons if it is more basic. Acidic means accept the electron, basic means donate the electron. So if the ligand is more basic, it will be, complex will be more stable. Huh? Because it will form coordinate bond, that's why. Otherwise, it will not form that strong covalent coordinate bond. Presence of chelate rings also increases the stability. This is also asked very frequently, even in CBSE it is asked very frequently, that if you have, say...
Sir, what is chili ring?
Yeah, revising. Suppose you have this one, okay? In this case, you have En, En, En. Didentate, tridentate, polydentate are called chelate. So this type of bond is called chelate when it is more than one bonds from one ligand. Is that clear what I am saying?
Yes, sir.
So if any ligand forms more than one coordinate bonds with the central metal atoms at the same time, then it is called chelation. So this is chelate ring. Chelate ring. In this case, because one ligand is connected with two bonds at the same time, it is more strong and more stable as compared to single bonded ligand. Is that clear? So what points I have discussed? Three specific points I have discussed. Oxidation state higher, more stability. Basic character higher, more stable. Chelation, more stable. Size of the metal ion, smaller the size of metal ion, higher is the stability. Why? Very simple concept. If the size of the metal ion is smaller, the incoming electrons will be pulled by nucleus stronger. Okay, because these will be closer to nucleus. If the central metal atom is very large, then nucleus will not be able to attract these two electrons within the shell with that great force. So smaller the size of metal ion, higher is the stability. Electronegativity and polarizing power of the central metal ion also decides the stability. More is the electronegativity and polarization power of the metal ion, more stable is the complex. Why? Because the definition, by definition, electronegativity is the tendency to attract the shared electron pair. So if central metal atom is comparatively more electronegative or it has greater polarizing power, in both cases, it will be more stable. Because of the definition. Clear? Any confusion here? Next topic, organometallics. So just I am going back because this is asked and students are not able to answer quite frequently. First, I talked about oxidation state. Higher the oxidation state, more stable. Higher the basic character, more stable. Higher the chelation. Okay, chelation more stable, and higher the chelation, even more stable. Then I talked about smaller the metal atom because the electron will be closer to nucleus. And then I talked about the electronegativity and polarizing power of the central metal atom. Higher these two, higher will be the stability. Now organometallics. Organometallics means it is similar one. Central metal atom is there, but the ligands are organic compound. So instead of NH3, H2O, Cl, these will be organic compounds. These are called organometallics. Simple. So based on the nature of metal carbon bond, they are classified into means organometallic, sigma bonded. These are formed by main group S and P block elements. Remember, whatever I am telling you, that much is you need to remember. Don't go into too many details. In Pradeep, a lot of details are given and unnecessary details. Never ask. Okay, whether you consider it in CBSE, whether you consider in NEET or IIT, never ask. So sigma bonded organometallic compounds, these are formed by main S and P block. First two and last six. Sigma bond. Elements, non-metallic and metalloid elements, for example, zinc, cadmium, mercury, through a normal 2-electron covalent bond, for example, RMgx, and you know RMgx, CH3, Mg, Br. Or on zinc, you have 2 ethyl groups. So it is still central metal atom, and the connected ligands are organic compounds, or you can say alkyls. So that's why alkyl groups, that's why it is called organometallic, and it is sigma bond. Then it is pi bonded organometallics, pi complexes. You just need to remember the names of the examples here. These are formed mainly by transition elements. Transition elements, D block elements. The point here is important that normally, if I say complexes, those are pi complexes. Sigma bonded, if I say, I'm going back. Sigma bonded. These are formed by main group S and P block elements. And remember, these are not complex compounds. These are organometallic compounds, but these are not actually complex compounds. Complex compounds are formed by D block, and those are pi complexes. Okay. So these are formed mainly by transition elements. Transition elements means D block elements. Pi complex. Here, normal sigma bond is formed through the pi cloud of electrons of the organic molecules. Pi cloud means p orbitals. Okay. Examples you need to remember: Z salt, which is KPtCl3 eta square C2H4, and then ferrocene Fe eta 2 power 5 C5H5 whole square. Nothing else you need to go into detail what this eta means. This signifies the how these are connected, but that's not in your syllabus. Just still write the examples. I will give you some idea about how the interaction takes place between the clouds, how sigma bond is formed and how pi bond is formed. But first write these examples. MCQ type questions are asked based on this particular part. Normally subjective questions are not asked, so you will not see asking something like what are these and give example, but yes, MCQ question will be there. Then pi and sigma bonded organometallic compounds, metal carbonyls. So here specifically I am talking about metal carbonyls. So the ligand is CO. Ligand is CO. Mainly these are formed by vanadium, chromium, molybdenum, tungsten. Vanadium, chromium, molybdenum, tungsten. This is sometimes you might be asked, so you need to remember this is synergic bonding. The synergic word in English means that both help each other. Synergy in English means both help each other. So if Samad helps Kavish and Kavish helps Samad, so both get something, right? Both get benefited. The same thing happens here. And the concept, very important, why this is important, the concept of back bonding also. This is an example of back bonding also. And back bonding is important from competitive examinations perspective. Not too many questions asked in CBSE, but because not too many questions asked in CBSE, IIT professors are very much fond of asking questions on back bonding. So metal carbon bond in metal carbonyls possess both sigma and pi bond. How sigma bond is formed? Sigma bond is formed by you have carbon here, okay, carbon. So carbon has 1s2, 2s2, 2p, 2p. So the electrons first, just explaining it. Its formation involves following steps. So first I am talking about how this bond is formed, this bond. Okay. There is an overlap of filled pi 2p orbitals of CO, means in this I have carbon 1s2, 2s2, 2p, 2. So I have here in p, I have electrons. So these electrons, 2p electrons, which are parallel, obviously, pi electrons, they give their 2 electrons to empty orbital of metal. The orbital empty, there will be empty orbital of metal. So these 2 electrons will be given and carbon will form the sigma bond first. Then what will happen? Then it is important point. What will happen? The metal has pi electrons here. So the metal pi overlap involving filled metal d orbital and empty anti-bonding pi 2p orbitals of same CO. So these are pi anti-bonding orbitals. Molecular orbital theory can you recall from 11th grade? We talked about molecular orbital theory. Anyone else? Molecular orbital theory. There were bonding orbitals, anti-bonding orbitals. Okay. Bonding orbitals were those ones which actually help in making the molecule stable, and anti-bonding means they make the molecule unstable. You remember we calculated the bond order, bonding electrons minus anti-bonding electrons divided by 2. Okay. But I'm not going into those details. So there will be anti-bonding orbitals here. And see what happens. The d, remember this is pi electrons of d orbital. So this is d orbital. 4 d orbital. These will give their electrons back to empty anti-bonding orbitals of the carbon. So read this statement and memorize this statement, what I am saying, because it will help you to explain the back bonding. And why do we call it back bonding? It happens not only here, it happens in many cases, but this is one example. There is a pi overlap. This is pi overlap. Okay, this. First, we talked about this one. I am not talking about this one now. I am talking about what's happening then next. There is pi overlap involving filled metal d orbital. So here we have d orbital, d orbital. Okay. Those 2 electrons will actually go to the empty anti-bonding 2p orbital of same CO. Because it is giving these 2 electrons back, so this carbon helped the metal to have coordinate bond. Then metal helped back the carbon to form the pi bond. So sigma bond was formed by what? Sigma bond was formed by carbon, and sigma bond is formed first. So sigma bond formed first, and then metal formed the pi bond back with the anti-bonding pi orbitals of carbon. So that's why it is called back bonding. The reason it is called back bonding is because the metal, after the sigma bond is formed, the metal forms the pi bond with carbon of the carbonyl group. Okay. So in all such cases, where first sigma bond is formed and then other pi bond is formed, or even if pi bond is not formed, there is some interaction. Okay. So sometimes pi bond might not be formed. There will be just some interaction. Even then that will be called back bonding. These are some examples which you need to remember of metal carbonyls. Specifically these ones you face problem if they appear. Write down the names. You can obviously memorize these afterwards from the notes, but at least write down the names, metal carbonyl names. Slightly theoretical part, but you have to remember. When I am saying you need to remember few things which are not even in CBSE, it will be required to understand the concepts I will be talking about later on for IIT and NEET. Otherwise, it will be a lot of problem for you. Directly, you will not be able to understand IIT part, NEET part, if you don't understand right now something beyond CBSE. Now the question, explain on the basis of valence bond theory that NiCN-O4 2- ion with square planar structure is a diamagnetic and the NiCl4 2- ion with tetrahedral geometry is paramagnetic. This is something, it is just I am checking. We have done this question. Okay, very similar question we have done. I am just checking whether you are able to do this question or not. Just everyone, you will do this question and will send the screenshot to me. Start doing it and send the screenshot to me. I can't wait. Now understand. You have nickel. Okay. What will be the configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Right? Then you will see what is the oxidation state of nickel here. It is x minus 4 equals to -2. That is x is plus 2. We will write configuration of nickel 2 plus. This will go away. Outermost shell will go away. So here it will be just 3d8. So 3d8 will be like this. And Cn is a strong field ligand. So if it is a strong field ligand, pairing will take place. And it will be like this. Clear? If it is like this, then the 4 CNs will go in this D, and then S of 4s, which is now empty. 4s electrons gone, that is empty. And then 3p will be here, but you will use only 2p because you need just 4 cyanides, 4 cyanides. So 1d sp2 and dsp2 is square planar. sp3 is tetrahedral, dsp2 is square planar. We talked about it in the very beginning. So here you will say because it has dsp2 hybridization, it will be square planar. And then for diamagnetic, there are no unpaired electrons. So no unpaired electrons. It means it is Is that clear? Yes, Sharma. Is that clear or not? You are still sleeping. Now NiCl4. NiCl4 also nickel is in +2 oxidation state. Oxidation state is same. But in this case, chlorine is weak field ligand. So nickel configuration will still be same. It will be D8. But it will remain like this. There won't be any pairing. Because there won't be any pairing, now you have next 4 as S and these 3P. 3. So it will be sp3 hybridization, and sp3 is tetrahedral. So that's why it is tetrahedral. And because we have unpaired electrons, it is paramagnetic. Next question. NiCl4 2-, which we have already written the configuration for in previous question, is paramagnetic while NiCO4 is diamagnetic, though both are tetrahedral. Both are tetrahedral. Okay. The reason is nickel here is in 0 oxidation state. In this case, we have talked about the configuration is like this. Obviously, NiCl4 is paramagnetic, unpaired electrons. Now consider this one, CO4. CO is a strong field ligand or weak field ligand? A strong field ligand, right? So even if it is 0 oxidation state, you don't consider. In another question that is the case, not in this case. You have the configuration here as nickel, and it is 4s2 and 3d8 still. But because it is a strong field ligand, pairing will take place. So configuration will be like this. But if a configuration is like this, it should be dsp2 configuration and it should be square planar, isn't it? It should be here D and then S and then P. But remember, there are electrons in S. There are electrons in S. It means this configuration is not possible that D and then you don't use S and you use P. The reason is there is the difference in these two energies. If there are successive orbitals in which the energy difference is very low. So from here to here, it is very low energy level. From here to here, it is very low energy level. So they can combine to form hybrids. You know the rule that those orbitals combine to form hybrids which are degenerate, means these have very close energies. But here, if you remove the middle one, 4s2, these two comparatively will not have that much close energy. They will not combine to form hybrid. It means the hybridization cannot start in such a way that it will be D and it will be P. So now coming back to the question, both are tetrahedral. So what actually happens? These two electrons move to this D. When hybridization happens, these two electrons move to these two. Why? Because these two have close energy. And then sp3 configuration takes place. Is that clear what happens in this case? Specifically, different question. You need to remember the hybridization cannot be like dp3 like that. dp3. Hybridization can be with close orbitals only. You cannot skip the orbitals. So in this case, what happens? To have the closed orbitals to form hybrids, the s electrons move to d orbital. And then sp3 hybridization happens. So it causes the 4s electrons to shift to 3d orbitals, thereby giving rise to sp. Fine. And this question is very much common, and normally students skip this question. You should be able to do it. Next, FeS2O6 3 plus is strongly paramagnetic, whereas FeCN6 3 minus is weakly paramagnetic or feebly paramagnetic. Why? And the reason is very simple. Greater the number of unpaired electrons, greater the paramagnetism. So it means in this case, you have greater number of unpaired electrons. In this case, there will be unpaired electrons, but not those many. Less number of unpaired electrons. So in case of FeS2O6, okay, Fe exists in both cases in +3 oxidation state. Here, whatever you have is on Fe because this is neutral, H2O is neutral. Here it is x minus 6 equals to -3. So again, x equals to +3. In both cases, it is +3 oxidation state. And iron 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So this is the configuration. Here Fe3 plus. So Fe3 plus will be, this will go away, and 1 electron from here. So 2 electrons from here, 1 electron from there. So Fe3 plus will have D5 configuration. But in case of H2O, and in case of Cn minus, which one is a strong field again? Cn minus. So in case of FeH2O, pairing will not take place. It means it will remain like this. But in case of Cn minus, same Fe will be like this. So in this case, we have 5 unpaired electrons. In this case, we have 1 unpaired electron. So if you calculate mu here, dipole moment, it will be n plus 2, that is square root of 35. You know square root of 36 will be 6. So square root of 35 will be approximately 5.9 Bohr magneton, and here it will be square root 1 plus 2. That is square root of 3. Square root of 3 is 1.732. Clear? So paramagnetism will be very high in case of FeS2O6 3 plus, less in case of FeCN6 3 minus. Next question. Explain CuNH3O6 3 plus is an inner orbital complex, whereas NiNH3O6 2 plus is an outer orbital complex. Before you start, what does it mean? Inner orbital complex, outer orbital complex. I explained in previous class. Write in your notebook and in your chat box. Write the meaning of inner orbital and outer orbital complexes. Everyone, write it. Ariman, very good. That is the answer. Tanishi, yes, that is an example, but yes, you are writing it correctly. It means you know, right? Inner d orbital means you are using d orbital of the previous shell. Okay, so if it is something like this, d, s, and these p orbitals being used. So this is say 3d. You use d of 3 and you use this 4s, and p you use of this one 4px, 4py, and This is 3D. So it is DSP2, for example. So because here D is of inner shell, it is inner complex. But if it is something like everything here, sorry, is filled, you have SP3 and then D of the fourth shell. So you have S here, you have P, 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 and then D. Say it is D2. Here you are using SP3, D2 configuration. Here D is of outer shell, fourth shell. So it will be outer complex. Clear? So outer orbital complex, inner orbital complex, this is the difference. So it means what you need to show? You need to show that in this case, it will be configuration, hybridization, in which case the D orbital of inner shell will be used. And in this case, the D orbital of outer shell will be used when you simplify it. So how to do that? In case of first, okay? Cobalt when you write. I should have that one. Understand it. And a little bit tricky also. I will explain it. In case of CuNH3 whole 6, oxidation state is +3 here. So you will write the configuration here. 4s2 will go away. And 1 electron from here will go away. So you will have 4 unpaired electrons. NH3 is a strong field ligand. Okay, it comes closer to En. Pairing will take place. And here you have D2sp3 configuration. All 6 you need. Okay. So all 6, this one, this one, this one, this one, all will get electrons from NH3. So D being used is of inner shell. So we'll say hence it is inner orbital complex. In case of NiNH3, whole twice, this is nickel here. It is in +2 oxidation state because NH3 is neutral. Again, these 2 electrons will go away and it will be D8 configuration. Nickel in +2 oxidation state, D8 configuration. Now pairing will take place again. Okay. Now again, as I said in one of the cases that there cannot be break in any orbital. So it cannot be D and then S you can miss and P. So it cannot be D, P hybridization. Another case where it can be. Here you have a D free, you have S free, you have 4P free, you have 4D free. But what actually happens here? This D orbital still does not take part in hybridization. Okay. Then only one 3D orbital is empty, thus it cannot undergo DSP. The reason is, try to understand what is the reason. If I use this configuration, the configuration will be, I need 6 NH3. So I will be using this one, these 3, and this one. The energy difference between this D and this D is quite large. For orbitals to form hybrids, they should be degenerate. This is thumb rule, remember always. Only degenerate orbitals form hybrids, means all have very close energy. So the energies must not be very different. In this case, the difference between overall difference in these two will be very, very high. And the reason is very simple, because if you add here 3D, it will be 3 plus 2, 5. Here it will be 4 plus 2, 6. Moreover, this 3 and this 4 will make the difference of the shell, whole shell. Okay. Here, if you see 3D and 4P, it is 4 plus 1 is still 5. So that's why it is still closer. Okay. So these can combine, but these all cannot combine. So what happens? The hybridization starts from here. These 6 will be considered, and the configuration is sp3b2, which is outer complex. Okay, outer orbital complex. Is that clear what I am saying? Okay. So in both cases, when I said in previous case, I said one configuration hybridization was not possible. In that case, there was 4s filled. So you cannot have a break. All the orbitals should be empty in sequence, first of all. Okay. So I'm just going back to explain that one also. Yeah, this case. So in this case, what will happen? This one will become empty. CO is a strong field ligand. But you cannot have the hybridization with orbitals which are not consequent. Okay? Consecutive, sorry. So this one is in between. So this hybridization cannot be. So you cannot say D P3. It cannot. Okay. So there must be empty consecutive empty orbitals. So that's why here it was not possible. These 2 electrons, that's why they moved here. So it was like this. Okay, because this electron moved here. After that, these 2 electrons will move here. Now you will have sp3 all empty. So sp3 will be there, that's why. So this was one case, and another case where hybridization cannot exist is this one which we talked about right now. Clear? So d orbital of inner and d orbital of the valence shell, both cannot be in same hybridization. If that is the case, inner one will not be considered. The hybridization will start from 4s, and then whether you need 6 or 7, whatever will be considered. Clear or not? Any confusion here? Okay. These questions actually make difference. If you can do these type of questions, 95% students will not be able to do these questions. I am telling you with my experience. Now predict the number of unpaired electrons in the square planar PD CN4 2 minus. Again, very simple question. You will write the configuration of PD plus 2. It will be of D8 configuration. D8 configuration will be like this. I'm not going into details. You should memorize these structures. Okay. There are very few transition elements which form complexes we are talking about. So normally you might see that we are talking about cobalt, chromium, iron, palladium. Okay. So you need to remember these configurations specifically. So D8 configuration is there, and CN is a strong field ligand. Pairing will take place. So predict the number of unpaired electrons because pairing will take place. So this electron will move here, and here there won't be any electron. So no unpaired electron will be there actually. No unpaired electron. Next is amongst the following, the most stable complex is. Now you will use that, as I said, that question is asked in MCQ type question. You will tell me by using those concepts whether higher oxidation state is applicable, whether basic ligand is applicable, okay, whether chelate ligand is applicable, whether a smaller central metal atom is applicable. Are you getting it? We talked about? Huh? Just think about it. It's basically very, very easy question. Very, very easy question. Which one will be most stable? No. Okay, why? Because of chelation. The third one has oxalate, and oxalate has chelation. We will apply simple concepts I told you. I told you 5 points just to memorize. So here in this case, the answer is chelation in the oxalate.